Hello guys, today we start to study chapter 9, the atom. This chapter contains 14 sections, divided into 4 parts. We will learn about quantum theory of light, matter waves, the hydrogen atom, and the quantum theory of atom. When a light with frequency high enough shines on a metal surface, electrons are emitted. This phenomenon is called photoelectric effect and conflicts with the wave theory of light. To explain the photoelectric effect, Einstein in 1905 proposed that light is composed of photons, massless particles, each with energy given by E equal hf. Here f is the frequency of light, and h is the Planck constant, given by 6.62 times 10 to the negative 34 joule second. He then explained the photoelectric effect based on the photon energy to be equal to the kinetic energy of electron plus the energy needed to pull out the electron from the metal. Einstein won the 1921 Nobel Prize in Physics due to his equation of photoelectric effect. For an example, find the photon energy of light with frequency of 2 times 10 to 16 Hz. From the photon energy formula, E equal h times f, substituting the numbers of Planck constant and the frequency into the equation, we obtain the photon energy to be 1.3 times 10 to negative 17 joule. Dividing it by the factor of 1.6 times 10 to negative 19, we have the photon energy to be 82.75 electrovolt. According to the wave theory, light consists of electromagnetic waves described by wavelength, frequency, and so on. According to the quantum theory, light consists of photons, massless particles described by energy and momentum. Therefore, light has dual properties, i.e., both wave and particle features. To a particular event, low-frequency light behaves more like a wave, such as radio waves, microwaves, while high-frequency light behaves more like a particle, such as X-rays and gamma rays. X-rays are extremely high-frequency electromagnetic waves with frequency greater than 10 to 18 Hz. They are generated when high-energy electrons are suddenly stopped on a target. Roentgen was the first one to accidentally discover the X-rays in his lab. Being hinted at the dual properties of light, de Broglie suggested that a moving particle might behave like a wave, called the de Broglie wave. The wavelength of de Broglie wave for a particle with mass m and velocity v is calculated as the Planck constant h divided by the particle momentum mv, i.e. the wavelength lambda is equal to the Planck constant h divided by the momentum mv. For an example, find the wavelength of a flying golf ball with mass of 0.06 kg and a speed of 100 meters per second. From the de Broglie wavelength formula, substituting the numbers for Planck constant, mass, and velocity into the formula, we obtain that the de Broglie wavelength of the golf ball is about 10 to negative 34 meters. which is much smaller than the size of the golf ball. That is why the wave property of a macroscopic golf ball is not significant or not detectable. For an electron moves at 10 to 7 meter per second, however, the de Broglie wavelength can be about its radius. Therefore, in atomic scale, the particle's wave property can be significant and detectable. The Broglie wave is neither a mechanical wave nor an electromagnetic wave. It is a wave of probability described by a wave function whose modulus square determines the probability density of finding particle at that point and in the time. In the quantum theory, a moving particle is described as a group or packet waves that travel at the same speed of the particle. With wavelengths about the size. Since a moving particle behaves like a wave, then it is impossible to measure or determine the exact position and the exact momentum at the same time. This is called uncertainty principle, discovered by Heisenberg in 1927. According to this principle, we cannot know the exact position and velocity of a moving particle at the same time. We can only tell the probability of finding particle at the position in a given time. A gas is called excited gas if its electrons have absorbed extra energy. An excited gas can emit light. The spectroscope is an instrument that can disperse light emitted by atoms of an excited gas into different frequency or colors, called atomic spectrum. Various frequencies of light emitted by an excited substance are called the emission spectrum. Various frequencies of light absorbed by a substance when light passes through are called the absorption spectrum. Both emission and absorption spectra are discrete and fallen into sets and series. And these properties of atomic spectra cannot be explained by the classical physics. To explain the atomic spectrum, Bohr, in 1913, suggested that electrons in an atom possesses a specific energy level that depends on their orbit. The innermost orbit has the least energy, and the electron rises to a high energy level by absorbing a photon and falls to a lower energy level by emitting a photon. The spectral lines and series can be seen or understood from this diagram. We can see Raman theorem, Bauman's theorem, and so on of the spectrum. The orbit of an electron is constrained such that the perimeter of the orbit is equal to a whole number of the de Broglie wavelengths of the electron. The innermost orbit contains one electron wave, the second orbit contains two electron waves, and so on. The nth orbit contains n electron waves. Laser is a device that produces an intense beam of a single frequency and a coherent light. A material, if its atoms have a metastable state, i.e. a state with longer lifeline, lifetime, can be used to make a laser. Triggering the laser material whose atoms have been excited to their metastable state produces a laser light beam. When those electrons suddenly jump to the ground state from the metastable state. Quantum mechanics is a theory developed by many physicists during the 1920s to describe quantization properties of the microscopic world. Newton mechanics is just a special case of quantum mechanics. In quantum mechanics, a quantum state of a particle is determined by a set of quantum numbers. There are 4 types of quantum numbers. The principal quantum number is for energy, denoted by n, and valued as the integer 1, 2, 3, 4, and so on. The orbital quantum number is for the magnitude of angular momentum, denoted by L, and valued as the integer from 0 through m-1. The magnetic quantum number is for the direction of angular momentum, denoted by ml, and valued as the integer from negative L through positive L. The spin quantum number is for the direction of the particle spin, denoted by ms, and valued as negative half and positive half. For spin half particles such as electron. The quantum states of particles are governed by the exclusive principle proposed by Pauli in 1925. It says that only one electron in an atom can exist in a given quantum state. This principle can also be equivalent to say each atomic electron must have a different set of the 4 quantum numbers. This is the end of the chapter. Thank you.